Welcome to the video tutorial for the Crash Carts Lab, otherwise known as the Conservation of Momentum Lab. I think we missed the transition here. Let me back up. There it is. Off to the left, I've got a screenshot from an ancient game for Windows called Carmageddon Carpocalypse Now, which I think came out in 1998, thereabouts. It was a precursor of that more modern, most depraved game, Grand Theft Auto. But in this game, you could smash your vehicle into other oncoming vehicles. It was great fun. I played it all summer, I think, in the summer of 2000, and realized that it was affecting my actual driving because if I was going down a two-lane highway, I would be suddenly overwhelmed with the urge to pull my car into oncoming traffic and smash into the vehicles approaching me. So I had to stop playing that game. So we will be not doing an experiment in the flesh, so to speak, but looking at some videos and analyzing them in Tracker. And each of those videos will involve a head-on collision between two carts, much like this one. Oh, were you worried? So let's start out by watching the video, or one of the videos, because you'll be analyzing several videos in this lab. And you will find each of these videos linked below the instructions within assignments. And they've all got names like this one right here, colliding carts. Don't worry about the numbers so much, but the initials here are actually very telling. Capital M means this one is more massive than this one, which is denoted by lowercase m, and the E, I believe, is for elastic, which gives you a big hint as far as answering some of the questions later in the lab. So here's this very short video. It's a one-dimensional collision between two objects, and we see that the carts are on wheels, and presumably these wheels have low friction bearings. So as we analyze these videos, we will make the approximation that there's no friction, no rolling friction between the cart and the track. Now keep in mind, rolling friction is a more complicated phenomenon than one might think just by reading this introductory book that we're using. But we can approximate it as being simply a force backwards that's proportional to the normal force between the cart and the track. But we're just going to pretend that there is no rolling friction. One reason it's actually preferable to do this lab with videos is these videos were produced in a really controlled environment with good equipment. And the equipment that we have at our school is a little beat up after years of usage. And so the results tend to come out much better, actually, by analyzing these videos. Let's watch that one more time. Observe that the second mass was at rest. They're telling us exactly the length of the track here to the nearest centimeter, hundredth of a meter, and they're giving us the frame rate. So remember, in Tracker, one of the things you have to do is tell the computer what the frame rate is. And since we know about momentum now, because we're well into the chapter on momentum, it's clear that the momentum of the cart on the left changes. Remember, since momentum is proportional to velocity, any change in velocity implies a change in momentum. And if we call to the right the positive direction, so the direction in which this first cart is moving, let's call that the positive direction, it's clear that the momentum of the first cart decreases because the positive velocity decreases, and the momentum of the second cart increases. So there's obviously an exchange of momentum there. Some of the momentum of cart A, you could say, is imparted to cart B. So that's the numbering or the labeling scheme that I'll stick with throughout the lab. This cart on the left I will call mass A or cart A, and this will be cart B on the right. How do I pause here? So let's give these carts some labels. And we'll analyze this frame by frame. Now, it's not obvious just from looking, but there are magnets mounted on the bumpers of these carts, which will allow them to interact, to push on each other without actually touching. And the advantage of that is if the carts actually bump into each other, we're probably going to hear a sound, for one, and sound waves require energy. which means that some of the kinetic energy of the incoming cart A is lost to sound waves. And that prohibits the collision from being what we call an elastic collision. We would like to analyze some collisions for which the kinetic energy, total kinetic energy, before and after is roughly the same. But if the carts are crashing into each other the way real cars crash into each other in a traffic accident, you hear the crash. And that means some of the kinetic energy of the incoming vehicles was dissipated as sound. Speaking of dissipation, there's also going to be energy lost to heating up. You might imagine that if you smash two vehicles into each other, if you were to go up and touch the bumpers immediately afterwards, they might feel a little warm because some of the kinetic energy is dissipated that way. Just like if you rub your hands together, you can feel the dissipated thermal energy. And also if there's any deformation of the vehicles, if the bumper or the hood is mangled, that takes energy. If you were to go up and do that with your hands, well, you'd need a tool. But if you were to take a baseball bat and smash up a car so that it looks like a car after an accident, that takes considerable energy. But if we allow these carts to repel one another via a magnetic interaction or electromagnetic interaction, we can avoid any loss of kinetic energy, or for the most part. So I am going to indicate that interaction with some cartoon symbols here. Don't take this literally. When you take the next class in the sequence and you learn about electricity and magnetism, you'll be introduced to the notion of a field, an electric field, a magnetic field. These silly little curves I've drawn here should not be taken literally as the actual field lines. But this indicates that the carts are now close enough to experience a small amount of repulsion. Hopefully you've all played with refrigerator magnets and you know that the strength of the repulsion between two magnets, if you've got their poles facing each other, is strongly dependent on the distance between the magnets. So as cart A approaches cart B, and also let's plop in some force vectors, and you'll notice that I've very purposely made this vector equal in length to this vector, but opposite in direction. Because we will assume that Newton's third law holds for this interaction. Remember, this lab is about confirming the validity of Newton's mechanics. So FBA, that would be the force of cart B on cart A. Cart B pushes back on cart A via this magnetic repulsion, and we are representing that interaction with this force vector. So FAB would have to be the force of cart A on cart B, and we are postulating that those force vectors are equal and opposite. Now, I pointed out in one of the lecture videos that Newton's third law is not a universal law that holds for all interactions and all circumstances. It's not difficult to imagine a situation where two charged particles are interacting in such a way that the force vectors are not equal and opposite. But here we've got two macroscopic objects, and we will assume that the third law is also valid. So as the carts get a little closer, I've indicated that the interaction increases in strength. That's why I've made the force vectors longer, but they're still equal and opposite. Here's where the carts reach their point of closest approach, and that's why I've made the vectors even longer, but still equal and opposite. So the force on each cart is changing in time. It's always changing, and so is, the force on cart A is changing, the force on cart B is changing, but the idea is that at any point in time, at any instant, those two force vectors will still be equal and opposite. And now they're rolling together. They begin to separate, so I've made the force vectors a little shorter still. Now the interaction has almost ended, but still the vectors are equal and opposite. And finally, they've gotten to a distance from each other, at which point the interaction is basically negligible. Because again, you may know from your experience with magnets that the force of repulsion is really, it's strongly dependent on distance. You don't have to pull them apart very far before you feel practically nothing. Okay, now what's going on here? Yes, let's assign some labels to two specific times. Here's the frame just before the carts begin to experience some repulsion. So here they're already pushing on each other. Let's assume this is the instant right before they begin to interact. That's where cart A has its initial momentum, which has not been yet changed by the force from cart B. Let's call that time 1, just before the interaction. And as soon as they have finished interacting and there's no more measurable force between them, we'll call that time 2. So it's important to note that those times are right before the interaction and right after. There's a couple frames in the video after this, but if you wait too long, then each of these carts will have experienced some friction with the track. And I also neglected to point out air drag, right? At any speed, the carts are going to experience some air drag. But let me back up. During this time that they're rolling together, yes, they are both experiencing a little bit of air drag, but the strength of the magnetic repulsion between them is probably significantly greater than that air drag. So during the time in which they push on each other, we can make the approximation that the air drag is just, it's negligible. I don't know what the actual numbers are, I haven't calculated that, but let's say it's 100 to 1. If the magnetic repulsion is 100 times as great as the air drag, then we might as well, for the purposes of this lab, just ignore the air drag. And in your book, that's called the impulse approximation. It captures the idea that during the time of a brief collision, whether it's a baseball bat and a baseball or two cars, yes, these outside forces are present, but they're insignificant compared to the rather large interaction forces between the two objects which are colliding. That's the impulse approximation, and we are using that in this lab. So now let's look at the theory. We've already invoked Newton's third law, and this is really a differential statement. You know what, let me save that term for a couple slides from now. Newton's third law is applicable at any point in time, at any instant. The two force vectors should be equal and opposite. Equal in magnitude, opposite in direction, hence the minus sign. And here's where we make the leap to another statement. I've just invoked the other of really the two core principles here in this entire semester. Newton's third law, Newton's second. Yes, there's also Newton's law of gravity, but I've suggested before that you could develop the entire curriculum of the semester with really just these two results and Newton's law of gravity. So let's look at the left side. This is the force that cart B exerts on cart A. So this is a force on cart A. I really should have a bubble around cart A right now. Now, again, we're pretending that there's no air drag and no friction on cart A. Yes, there's a normal force upwards, and there's a gravitational force downwards, but we're only analyzing the motion in this direction, along an axis perpendicular to the normal direction. So we're not really concerned with those forces. Plus, those forces would sum to zero. Since the cart is not accelerating in this direction, then the normal force up would have to balance the gravitational force downwards so that the net force along that axis is zero. So along this axis, the repulsion between the two carts is the only force acting on cart A. And remember, for any mass m, F equals ma speaks to the net force F. So since this is the net force on cart A, I can set that equal to the mass of cart A times its acceleration. So what I've done just now on the left side is replace the force on cart A by ma. I'm using F equals ma applied to cart A. We can do the same thing to the right side of the equation. Don't forget the minus sign. So FAB, that's cart A pushing back on cart B. So right now I'm looking at cart B and applying F equals ma to cart B. Since that repulsive force is the only force acting on cart B, then that force should equal mass B times the acceleration of cart B. The minus sign, of course, is inserted because it also appears over here. Okay, so it's important to recognize that I can only make that leap from this equation to this equation if we can also make the assumption that there are no outside forces, or that the outside forces sum to zero, okay? Because if you were doing a more precise analysis of this video, like if you had 500 frames per second, you might have to take into account the fact that there are a couple other forces on cart A, namely some small rolling friction and air drag. But we're pretending that, again, this is the only force on cart A. Okay, let's continue here. What is acceleration? Well, we spent the first month of the semester clarifying that. Acceleration is the rate of change of velocity. So I can rewrite the acceleration of cart A as the time derivative of cart A's velocity. Same thing for cart B. And since this is not a rocket ejecting fuel, remember the mass of a rocket is always changing because it's burning fuel and hence losing mass. But these two carts, there's no reason why the mass of these carts should be changing. And that means that we can put the mass inside the derivative. See what I've done there? You remember this from first semester calculus. The derivative of a constant times a function, you just pull the constant out front and then take the derivative of the function. That's what we're doing here. So since mass is a constant, I can move it in and out of the derivative symbol. All right, did I word that correctly? I can move it in and out of the parentheses there. And then of course we recognize this quantity, or you should recognize the product of mass times velocity. Remember, velocity is a vector. So if you scale a vector by this factor mass, you have another vector. That vector is called momentum. So we're really talking about the time derivative of the momentum of cart A over here on the left side. And now we can rewrite this in a very simple form. It's so satisfying. Simple, but all the physics is contained in this very direct, simple equation. It says that the rate at which cart A's momentum is changing must be the negative or the opposite of the rate at which cart B's momentum is changing. So qualitatively, it says that at any instant, if cart A's momentum is increasing, cart B's momentum must be decreasing. Of course, this equation is a stronger statement than just that. Not only does it say if one's going up, the other one's going down, it also says that the magnitude of those rates are equal. Again, so I've cleared the clutter here, and I'm going to move this equation over here. We can only make this statement in this particular situation because we assumed that there are no outside forces. So you could say that the cart A, cart B system is isolated. It's an isolated collision. During the collision, we can ignore forces like friction and air drag. Okay, now let's look at the units here. In the denominator on the left side, dt, well, that's a change in time, so the units are seconds. And hopefully you recall that the units of momentum, well, mass times velocity, that would be kilograms, meters per second. You can check that that's the same as a Newton second. I think it's worth memorizing that the Newton second is another way of expressing, sorry, I've got seconds in italics here and non-italics downstairs. The Newton second is equivalent to the kilogram meter per second. So when you're talking about how quickly momentum is changing, you're talking about the change in the number of newtons, the number of Newton seconds per second. How many Newton seconds of momentum are you gaining or losing per second? Okay, rate of change is Newton seconds per second. Well, of course, the seconds cancel, and you're left with newtons, which is force. So it's very intuitive. When you talk about something gaining momentum, let's say, you could quantify how many Newton seconds of momentum it's gaining per second. And that's equivalent to talking about the force applied to it, right? The harder you push on something, the more quickly it's gaining or losing momentum. I shouldn't really say gaining or losing because that makes it sound like momentum is a scalar. It's a vector. So perhaps I should say how quickly it's increasing or decreasing. That's, if you're talking about the momentum along one axis. Okay, now this is rather informal, what I've just done here. Imagine multiplying both sides of this equation by dt. If we regard the derivative as a fraction, a ratio of two quantities, We can multiply both sides by dt goes away, and we're left with this. And this says over a very tiny time interval, an infinitesimal time interval, dt, the change in cart A's momentum must be equal and opposite to the change in cart B's momentum. So just imagine a microsecond, which of course is not really infinitesimal, but it's a pretty small time interval. Remember that dp really stands for delta p. It's an infinitesimal change, delta p sub a. So this is what I like to call the Newton's third law version of conservation of momentum. It's one way of stating the conservation of momentum for a closed system of two masses which are interacting. Over a super small time interval, whatever the change in cart A's momentum is, the change in cart B's momentum must be equal in magnitude but opposite in direction. Simple as that. Now, if you integrate, which we'll do in a moment, or extrapolate that to larger time intervals, then you would call it delta p sub a. So again, I like to call this the Newton's third law statement of the conservation of momentum principle because it looks very much like Newton's third law. And it's super intuitive. If one cart gains momentum or has an increase in momentum, the other cart must have a corresponding decrease in momentum because the momentum has to be somewhere. It doesn't just disappear from the universe. If anything, it's exchanged, but it's not extinguished. It's a really powerful principle that you'll see in these videos. You'll see it in your spreadsheet when you're done crunching the numbers. And I was going to say miraculously enough, but perhaps that's not the right word. This same principle applies even to the interaction between subatomic particles, which is kind of amazing. You can watch protons collide with protons, maybe a proton colliding with a neutron, and new particles being created like neutrinos, which are often ejected from other subatomic particles during collisions. And if you keep track of the momentum, you find that this same principle applies, even for something so tiny. It even applies to light, believe it or not. Photons carry momentum. And if you have a subatomic collision between a particle of light and an electron, momentum is still conserved. So get used to this concept if you plan on studying more physics. Okay, so an exchange of momentum. Now let's actually show that more formally. Once again, the assumption of an isolated collision led us to this statement. The time derivatives of the momenta, that's plural for momentum, those time derivatives are equal and opposite. And when you see an equation like that, maybe you get the itch to integrate. So let's integrate both sides of the equation with respect to time. And of course, if we want to still have an equality here, we have to integrate between the same two limits on both sides. And here's where I've invoked those two labels that I showed you before. T1 will be a time just before the carts begin to push on each other and interact. T2 will be the time just after. So the interval between those two times is the interval during which they are actually pushing on each other. Now this is easy, right? What's the antiderivative of the derivative of p with respect to t? It's like these two operations undo each other. If you first differentiate with respect to time and then integrate with respect to time, you're back to your original quantity, which is momentum. So we evaluate cart A's momentum at the final and initial times and subtract. Same thing over here. Hopefully this is review for you. And here's a notation that you'll see during your unit on momentum. PA2, this is the momentum of cart A at time 2. This is the momentum of cart A at time 1. So I'm using letters to distinguish the masses and numbers to distinguish the times. Now, can we rearrange this equation? It's a little gnarly with all the subscripts there. Well, what is this quantity? This is final minus initial momentum for cart A. Inside the parentheses, we've got final minus initial momentum for cart B. So, of course, we can rewrite that as just delta P sub A. That's the change in cart A's momentum. That was the equation I wrote down just a few slides ago. Okay? The Newton's third law version of the conservation principle. Or you could shuffle some stuff around here. What I've done here is everything with the subscript 2, which is quantities at the final time, put those on the left side of the equation. Everything with a subscript 1, which is the initial quantities, put that on the right side, and we're left with this. Pardon me. Now, can we simplify this? Is there a more concise way to write this? Well, if we take cart A's momentum at time 2, cart B's momentum at time 2, and add them, we can call that the total momentum at time 2. Each cart has its individual momentum, but at any instant in time, if we add those two momentum vectors, we've got what's called the total momentum for the system being cart A and cart B together. And I like to use, or most books use, a capital P for that. Hopefully you can tell the difference. So capital P is the total momentum at time 2. Capital P sub 1 is the total momentum at time 1. And we have this remarkable statement that even though the momentum of each cart separately is changing, obviously as cart A slows down, its momentum changes. Cart B gets a little bump to the right, so its momentum is also changing. If you look at the total momentum of the system, it's the same at those two times. And we could go even further and show that it's really the same at any time, because I just arbitrarily picked the two times just before and just after the collision. You could even pick two times during the collision and show that the total momentum stays the same from one moment to the next. So these two statements are equivalent. Depending on which problem you're solving, one or the other might be more intuitive or easier to start your problem with. But they say the same thing. I got them from the same equation up here. But that's a really powerful principle, the conservation of momentum. You can't extinguish the momentum during a collision. It's got to go somewhere. You can find videos on YouTube of a giant commercial jet being literally flown into like a concrete wall that's anchored deep in the ground. So the jet, you know what, let me just pause and pull up that video. This looks like an older video, but here we are. Yikes. The video has no sound, but that must have been pretty darn loud. Now, if you apply the principle just discussed to this video, you may hit a bit of a conundrum, because if we call the direction to the right the positive x-axis, then obviously this jet is coming in with some negative momentum that's very large in magnitude. It's a heavy plane, planes move fast, and afterwards there's just a bunch of debris, right? If you wait for all that dust to settle, and it's not like the wall is moving, so after the collision there's nothing that continues to move to the left. The wall doesn't move, the plane doesn't move. So what happened to the momentum? If there was a large negative momentum before the collision, then where is that large negative momentum after the collision? Well, you can answer that by imagining that you're standing on the other side of that wall at a safe distance. What might you experience if you were standing on the other side of the wall? Well, it's going to be super loud. There's going to be some very powerful sound waves moving off to the left and to the right, but you can imagine there's probably some sort of shock wave. I don't know if I'm using the appropriate term, but you would likely feel seismic ripples beneath your feet. So that's a more advanced topic. It's really not one I've studied much myself, but you don't have to have chunks of mass flying through space in order to carry momentum. I mentioned that even light particles can carry momentum, and matter waves, I shouldn't say matter waves, that's quantum mechanics, sound waves, vibrations, those can also carry momentum. So your concept of momentum needs to be a little broader than just baseballs flying through the air or rolling carts to understand how the momentum is conserved in that instance. Let's clean this up. Here are the two useful ways of thinking about this collision. Either think in terms of an exchange of momentum, or simply that the total momentum is conserved. But always keep in mind, you can only use these equations if it's valid to say that there are no outside forces. It's got to be an isolated collision between those two objects. Now, even if you had multiple objects interacting, this is silly, but a car crash between 4 vehicles at a time, if you could ignore friction with the road or narrow drag, you could still say that the total momentum is conserved. In this case, you'd have 4 contributions on each side, but you wouldn't be able to make a statement like this. This one only applies to a collision between 2 objects. Now, for our purposes in this video, it really is a one-dimensional collision. If this is our coordinate system, we are really only looking at the change in momentum along the x-axis. Let's go with calling the direction to the right positive. Remember, this vector equation is a compact way of writing 2 or even 3 equations simultaneously. If you were to look at just the x component of this equation, it would look something like this. So it's really getting onerous with the subscripts here. PA2x, this is the momentum of cart A after the collision in the x direction. Now in our spreadsheet, we're not going to worry about the subscript x because it's understood that it's a one-dimensional collision that takes place along the x-axis. And now I think it's time to actually look at how this is done in Tracker. So here I am in Tracker. I've dragged and dropped the video file into the window. When you're ready for the next video file, you can go up to File and close the particular tab that you're working on. You could just restart the program. And remember, the first thing you might want to do is tell the computer what the frame rate is before you forget. So I go up here to the clip settings, and okay, I guess whoever made the video somehow included some metadata there. It already knows that the frame rate is 10 frames per second. You might have to update that yourself. And the computer does not know what the sense of physical scale is. So I will grab a calibration stick here, and it's telling me shift-click to mark end 1. So I hold down shift. Let me zoom in here. Oops, that didn't work. How do I zoom? I always forget. It used to be that you could use the scroll wheel, but now that's changing which frame we're at. 200%? Okay. That way I can be a little more accurate. Hold down shift, click on the left side here, and then I'll go over to the right side, shift click again. There's my calibration stick, and it's making the strange assumption that that's 517 meters. Your velocities will come out very strange indeed if you leave that number. You'll get some really high velocities. Let's change that to 1.0, number lock, 1.00 meters. Change the length unit to 1, confirm. Okay, now that you've done that, hide the stick. You're going to create problems if you leave it there. So it's hidden, but the computer now knows what the length scale is. We'll zoom back out here. And let's set up our axes. It looks like the x-axis is already pretty well aligned with the track, but I think there's some room for improvement. I guess I'll zoom in again. And it's not really important where you put the origin because we're interested in the velocity. Shifting the origin around is just going to move your graph up or down, but it won't change the slope. So don't sweat the location of the origin. And so let me tilt this just a little bit so we can be as accurate as possible. That should be fine. Oops. You get the idea. Hide those as well. You definitely want to get rid of those. Now, if you had accidentally rotated those axes and stuck your x-axis up that way, that would lead to problems because it would mean this direction was really the y-axis, and you would have to set the plot to show y versus t in order to analyze that. So try not to do that. And now let's just grab the clips or the frames that we're interested in. So the cart has just started moving. I'm going to start right here, ought to be good. And we don't need the last couple frames because the carts have already separated. You could grab them all. This clip is so short, it really doesn't matter. So I'll cut it off right there. And now let's create a point mass. Now, if you want to be a sophisticated tracker user, in other words, more sophisticated than me, you're welcome to create 2 point masses, one for each cart. I think that's unnecessary. I'm just going to create 1 point mass and call it cart. I don't want to call it mass A because that might confuse me. Remember, we've already labeled the left cart mass A and the right cart mass B. Let me just call it cart, because I'm going to use that same point mass to track each cart. I think that's simpler. All right, now, because the background is so simple, we should be able to get away with using auto tracker. Oops, I seem to have changed my beginning frame here. Okay, now if I recall, is this the auto tracker? Yeah, show auto tracker. And if you just hold down Shift, you get that square. That's for manual tracking. I would like to do the auto tracker, so it's Control Shift. If I hold down Control Shift, and let me zoom in again, Control Shift, I get the circle. I'll click on, how about the yellow dot? They probably put that there on purpose to make it really easy to track. So these are, within the circle is the pixels that I'd like to locate, and I guess I could scoot that up a little bit because those pixels aren't going to change. That circle doesn't grab any of the pixels off the cart. They're all on the cart, so that shouldn't change at all. And there's no need to look up here or down here for those pixels in the next frame because we know that the cart is rolling forward. And actually, yeah, okay, I do need to account for that. Since I've seen the video and I know that the cart doesn't bounce backwards, I don't need to look for those pixels back here. So this should be more than sufficient. Just in case, let me give it a little extra distance. We know that the cart's going to scoot forward in the next frame, but it's not moving that fast. I expect these pixels to be somewhere in here in the next frame. I will hit search now. And look at that. Auto search or auto track had no problem tracking the cart. So I'll close out of here. Now, if it didn't go well, you can right click, I believe. Yeah, if you right click on one of the points, clear steps would be a good way to go, and you can just start over. I think that's the easiest thing. If your software gets stuck, just close it out and restart. And look at that, we've got a beautiful graph of position versus time. I can tell immediately that the velocity of the cart changed during the collision. You can see how the slope has a distinct kink in it, and I can always do that, resize the windows if I want. Make sure that you're plotting X versus T. Right click, we go down to Analyze. Oh, I forgot, this is the part where you can't actually see, so hang on a second. Once again, right click, Analyze. There's the window that I wanted. And now is the time to ask for a best fit line. Remember that the slope of position versus time gives you velocity. We need the velocity of the cart just before the collision and just after the collision so that we can calculate its momentum. So we go up here to Analyze once again. Curve fit, a line is just a special curve. And this looks wonky. The computer is trying to fit a single line to all of this data. Well, obviously, we know that the velocity changes just before compared to just after the collision. So let's click and drag the data that we want. And here is where you need to be careful, because it looks to me that the line is already kinking right here. And that means we're looking at the time during the collision. I think that these points are, I think it's probably safe to assume that those points describe the velocity of the cart, or the position of the cart, before it begins to interact with cart B. I've intentionally left off this point because we're only interested in the velocity right before the collision. If you think about it, if you go back like two seconds before the collision, or 1 second, the cart is already slowing down due to friction and air drag, just a little bit, but we don't want to see any change in velocity due to friction or air drag. So get the velocity right before the collision and right after. That's why I've chosen to leave off, excuse me, this first point, or maybe first 2 points here. And arguably you could just grab these two, because this third point may already be during the collision. But it looks to me like that line's not going to be altered by that third point. So that looks good to me. I go down here, 5.14 E negative 1. Remember that E negative 1 means times 10 to the negative 1. And you'll want to confirm that you're doing a linear fit here, nothing like a parabola. So if we take the decimal point 1 to the left, that's a velocity of 0.51. I'll keep 3 digits, 0.514. I think it's unnecessary to keep that last. Yeah, you can keep the 2 if you want. So now it's time to go into our template spreadsheet in Excel. This template spreadsheet is available in assignments. It's going to be up to you to fill it all out. And you'll notice at the bottom I'm asking you just to give a 1-sentence, maybe 2-sentence description of the collision. So maybe we should revisit the video. And I neglected to point out that both carts are 500 grams. I think it tells you that at the beginning. Let's check that. I take that back. Yeah, definitely not. You'll want to use the numbers that are given here. Okay, don't forget a gram is 1,000th of a kilogram. It's a millikilogram, as I like to say. So I'm going to put the masses in right now. So cart B is the one on the right. That's 524 grams, so that's 0.524. 0.524. Let's go with SI units. That'll keep things as simple as possible. And mass A, what was that? 1,048. That's 1.048. And that mass is going to include the brick on the top there. 1.048. And those numbers will likely change for some of the other videos. So as we go across the row, that's all the data pertaining to that particular video. Now, how should we describe this collision? Okay, I could say something like a more massive cart collides I say elastically because you can see that they didn't actually bump into each other. They repulsed each other magnetically. So it collides elastically with a less massive stationary cart. Stationary meaning it was just sitting there to begin with. And if you want to be more precise and say, well, the massive cart was moving to the right, it slowed down due to the collision, and the stationary cart picked up speed to the right, yeah, that would be good too. Just 1 or 2 sentences is all I need. And for the velocities, well, right now I'm looking at cart A, right? I did the auto tracking for the cart on the left, which was cart A. So VA1, that would be the velocity of cart A at time 1. That's before the collision. I believe that was the number, or that's the number I was just looking at. Remember, this is the slope just before the collision, 0.5142. I'll be a little OCD and keep all the digits. I suppose since we've got 4 digits for mass A, then it's justifiable to keep 4 digits for the velocity. As for the velocity right after the collision, I'll click and drag across a different set. Now, I do not want to include this point because that's clearly during the collision. I think it would be safe to grab these, or perhaps even just these. There's no need to grab the points over here because by that time, cart A is rolling on its own and it's beginning to slow down just a little bit because of air drag and friction. But if we want to use the impulse approximation, we're only interested in the velocities at the very beginning of the collision and the very end. Okay, now I see that the slope is, in SI units, 0.1658. So it's clear from these numbers that cart A was moving to the right, hence the positive velocity, and it slowed down. Now here's a word of caution about sign. Both of these slopes are positive, indicating that both velocities for cart A are positive. And that's because when I set up my coordinate system, remember I had the x-axis pointing to the right. Now, you may accidentally get your axes flipped around, in which case your velocities would come out with a minus sign. So, you're welcome to, you can just take these numbers at face value, but the safe thing to do would be to ask yourself, should this cart's velocity be positive or negative? If it's moving to the right, let's call that positive. If it's moving to the left, let's call that negative. You should do a mental check before putting your numbers into the spreadsheet to make sure that your velocities have the appropriate sign. Now it's time to find cart B's velocity before and after the collision. So I will close out of the data tool here. We'll go back to tracker and I will clear all the steps. So right click on one of these points. Let's return to the beginning frame. Oops, I did it again. Why do I feel like I'm singing a Britney Spears song? Doesn't she say that in one of her songs? And I'll go back up here to create point mass. Oops. I did it again. Let's delete this here. I don't need that. So cart A. Let's now use this point mass to track cart B. Not cart A, cart B. Control Shift. See, I get that circle, click on there. I suppose I should zoom in just a little bit. I'm sure you understand what we're doing now. You could probably finish the spreadsheet on your own, but I'll say a few more things. Auto search. Oh, okay, so I actually did a sloppy job there. Delete. Let me just, clear all. There we go. Let's try that again. So it does help to zoom in and choose your pixel template more carefully. Control Shift. So let me scoot that up and just grab pixels that are on the cart. Make sure I've got plenty of room in the forward direction and search one more time. Okay, that time the computer had no trouble tracking it. Right click, analyze, nice graph. You can see where the cart B is gaining speed. By the time we get to about here, the cart has acquired, it's finished interacting with cart A and it has acquired its max speed. I'm not going to grab these points because by then the cart B should be slowing down just a little bit because of air drag, etc. Okay, now you don't actually need to grab these pixels before the collision, or these points before the collision, do you? You know that the cart's velocity is 0. So if you know it's 0, it's unnecessary to do that. Just enter 0. And this velocity looks like 0.6667. I could just round that. Linear fit, okay, everything looks good, 0.6667. I go back to the spreadsheet. That's the, 0.6667. That's at time 2. Before the collision, cart B was just sitting there. That's not going to be true for every video. In fact, some of the videos, I think the carts are moving towards each other, in which case cart B would have a negative velocity before the collision, so you would have to include that minus sign. Be careful with your signs. Remember, momentum is a vector quantity. Okay, so the tedious part is really just collecting these numbers, as I've just demonstrated for the first video. So that may take you a little while. Here's my suggestion, since your lab group is 3 people, why don't you Zoom conference? Share your screen. One person can have the spreadsheet pulled up. Another person can be doing the work in tracker. Maybe the third person is barking orders. However you want to do it, you can make this pretty quick. Team effort. But once that data is collected, the rest is easy because you're just going to enter each of these formulas in the top cell once and then iterate them. So PA1, take a guess what that means. The momentum of cart A at time 1. Okay, well, we know momentum is mass times velocity. So that would equal mass A, that's the mass of cart A, times the velocity of cart A at time 1. Mass times velocity for cart A at time 1. Look how easy I made this for you. I've already entered the units. Hey, make your own spreadsheet if you want. Make it look nicer. Hit enter. See, we don't have to do this by hand with a calculator. There's the momentum in Newton seconds. We can see it's a rather small number. That's because the mass is kind of small. And after you've already filled in the rest of your data for the masses and the velocities, you can just click and drag. Of course, I have zeros, but that will immediately calculate mass A's momentum before the collision for all the videos. That's why we're doing it in a spreadsheet. Work smarter, people. For cart A after the collision, that would equal mass A still, mass A times the velocity of cart A after the collision. And there it is. That velocity or that momentum is clearly decreased. Now, I'm not going to fill out the whole chart for you, obviously, but let's, I guess I'll give you a big generous hint. Let's do the same thing for cart B before and after the collision. So the momentum of cart B would be its mass times its velocity before the collision. Of course, that's 0. You do want to enter the formula though, because you're going to iterate for the other videos. Equals mass B times the velocity of B after the collision. All right. So capital P1, what do you think that is? That should be the total momentum at time 1. I'll let you figure that out. Same thing for the total momentum at time 2. What I'd like to draw your attention to is this. Delta P sub A, that would be the change in cart A's momentum as a result of the collision. So that's going to equal. And here I will, just to be safe, I'll use parentheses. I don't think I actually need them. Open parentheses, that's cart A's momentum at the end minus cart A's momentum at the beginning, close parentheses. So cart A suffered a decrease in momentum by that amount. Remember, one of the ways of thinking about this isolated collision is as an exchange of momentum. So if cart A lost 0.36 units of momentum, perhaps cart B gained 0.36 units of momentum. So equals, open parentheses, mass, or cart B's final momentum minus cart B's initial momentum. Okay, so the numbers aren't quite the same. They agree to the 10th place, but not the 100th place. But it's pretty clear here that there was an exchange of momentum. It was close to being exact. Almost the momentum lost by A was gained by B. Now, what's the reason for the discrepancy? Well, part of it is measurement error. We're using this grainy, low-resolution video with only 10 frames per second. Perhaps a high-definition video with more frames would yield better results. But also remember, the carts are contending with air drag and friction. But I'm hoping that this is already providing some compelling evidence for you that Newton's second law and third law, those are valid. They do a great job of explaining mechanical interactions at a scale much larger than the atom. You know, if you try to use F equals ma to explain the electron going around the proton, it really doesn't work so well. People started to realize that around the year 1900, and that forced them to seek out new physics, which you'll have to take 3C to learn about. Okay, or read it on your own. Now, percent delta capital P, what do you think that's about? That would be the percent change in total momentum. And I guess I'll go ahead and demonstrate this one. Well, the total momentum, yeah, I didn't mean to give you such generous hints here, but I'm afraid if I don't, it won't go so well. So total momentum before, well, that would be the momentum of cart A before the collision plus the momentum of cart B before the collision. Okay. Capital P2, that's the total momentum after. That's cart A's momentum after plus cart B's momentum after. And these numbers are a little different. we were expecting them to be, well, we were hoping they would be exactly the same because we expect momentum to be conserved. Well, they're only going to be equal to the extent that the impulse approximation is satisfied. If there really were no air drag and no rolling friction, I would expect these numbers to agree even better. Okay, percent change. Well, that's equal to the change compared to the initial momentum. So close parentheses, or open parentheses, that's the final total momentum minus the initial total momentum. So right now I've just entered delta P, that's capital P, the change in the total momentum compared to, in other words, divided by the total initial momentum. So it's the ratio of the change compared to the total. We can see that the change is, let's see, it goes from, I'm going to round to 0.54 and then 0.52. So it decreased by about 0.02 units of momentum. Is that bad? Is that good? Well, a decrease of 0.02 compared to 0.5, let me hit enter first. Why do I feel like I'm missing something there? 0.02, that's the ratio. Well, we'd like to express that as a percentage because that's how it's labeled. So multiply by 100. Okay, so the total momentum decreased by, let's just call that 3%. Now, I would like you to do this. This is too many digits. Right? We don't care about having five significant digits when we're talking about a percent change. So go up here and decrease this. I'll leave this up to you. 2 digits, 1 digit. I mean, that's perfectly fine. I guess I could go with that. I look at that and I think that's a drop of 3%. Now, again, that could be because of measurement error, or it could be an actual drop in momentum, total momentum, or decrease in total momentum due to the outside forces. But the point is, it's a small number. It's supposed to be rather compelling as far as, or compelling as evidence for the validity of Newton's mechanics. Okay, capital K1, I'll let you figure out what that is, or I'll just help you out. Capital K for kinetic energy. Notice it's not specifying cart A or cart B, so I'm really talking about the total kinetic energy. So this formula will be a little more gnarlier. It'll be up to you to implement, 1/2 mv squared for both carts, add them up. Over here, 1/2 mv squared for both carts. Notice the units are in joules, add them up, and then find the percent change in the total kinetic energy, just as I've done for the percent change in the total momentum. Now, there's no conservation of kinetic energy principle. That's not a thing. We do say that momentum is conserved in an isolated collision. Isolated is key. But we would only expect the kinetic energy to be, quote, conserved or constant before and after if it's an elastic collision. So this is all about seeing the difference between the elastic and inelastic collisions. Now, it's not going to be 100% or zero. Ideally, an elastic collision would have no loss of no loss of kinetic energy. So you're just looking for a qualitative difference. You should find that for the collisions that are supposed to be elastic, the ones with the magnets, the percent delta K should be a significantly smaller number than it is for the ones where the carts actually bump into each other. I think they've got Velcro on them. So it takes energy to deform the Velcro and have those little fibers lock. So you're looking for a significant difference in the loss of kinetic energy between elastic and inelastic collisions. I find this lab satisfying despite its simplicity because the numbers come out really nice if you're careful and tracker. And just try to keep in mind as you're doing it, what you're observing here is experimental confirmation of F equals ma. And here I'd like to point out, I should go back to the slides, hang on a second. The fundamental physics here, that's Newton's third law, and then we use Newton's second law to turn this equation into this one. Remember, force applied to a single particle, force is the time derivative of momentum. The harder you push on something, the more quickly you're changing its momentum. So this is what one might call the differential statement of the interaction here. You're equating the time derivatives of these two momenta, that's plural for momentum, the time derivatives of the two momenta at a single instant in time. So that's the differential statement of the interaction. But if you then apply calculus, apply the fundamental theorem of calculus, do a definite integral, then you're left with what you might call the integral statement of the interaction here. Again, the differential statement is merely that the rate of change of cart A's momentum is equal and opposite to the rate of change of cart B's momentum. The corresponding integral statement would be to say that over any finite time interval, in this case the time interval during which the collision occurs, any change in cart A's momentum is compensated by an equal and opposite change in cart B's momentum. These two are equivalent statements. You could use either as a starting point. When you're solving problems involving momentum conservation for an isolated collision of two objects, this is obviously the more convenient place to start. You can teach high school physics students to use this equation no problem. The connection between this statement and this statement is not intuitive. We're not born knowing it. It's not something that's so easily acquired by somebody taking an introductory physics course. But if you understand the basics of calculus, if you understand the fundamental theorem, you see how we went from one to the other. We just integrated. So as I've been saying already, that this entire semester, the curriculum of the entire semester can be developed using F equals ma, Newton's third law, and the calculus, just the fundamental theorem of calculus. It's really nice to see that when you can step back and recognize that that's what ties together everything throughout the semester. Of course, we also need one or two more ingredients, namely Newton's law of gravity, because many of the forces in F equals ma involve gravity. Okay, so the last thing I'll say is make sure to read through the instructions in assignments. There's a few conceptual questions you need to answer at the end, but those questions along with a plot. So for just one of your collisions, I need to see the plot that you produced in Tracker. There's a couple ways of doing that. Maybe I should go back to Tracker. And how do I get out of here? If I go into the data tool window, you could just maximize this, do a print screen. You can also go up here to, what is it, File. You could try exporting. Yeah, you guys probably know more ways of doing that than me, but you need to get your plot into a Word document, for instance. I do need to see the slope there, the equation of the line. So if you're not going to include all of this as a graphic, you need to type out the equation with these parameters that are given, because I need to confirm how you got the velocity of just one cart for one collision. I don't need to see the plots for every single collision. Okay, make sure to include that, turn it into a PDF. In that same PDF, you may as well put the answers to the conceptual questions. And lastly, I must have your spreadsheet. You can just attach that as an Excel file. Okay, don't worry about turning your spreadsheet into a PDF. Just attach the Excel file directly, and that should be all you need to complete this lab. Enjoy!